thanks for coming. Today, let's do a brief review of our Week 2's Numerical Analysis class. So in this week, we mainly talk about how to solve a univariate equation numerically, that is to find the root x to the equation fx equals to 0. We are mainly using iterative methods for finding roots. So what are iterative methods? It means that in order to get the root to a function f of x, we start with an initial guess x0 and then we generate x1, x2, x3 sequentially. We assume that the iterations converge the solution x star such that fx star equals to 0. That is to make the absolute value of xk minus x star goes to 0 as k goes to infinity. If the function f is continuous, then this will be the same as if the absolute value of f of xk goes to 0 as k goes to infinity. There are different possible stopping criteria because we cannot generate an infinitely long series. We have to stop somewhere. There is the absolute tolerance stopping criteria, which means that if the update between two consecutive steps is smaller than some small number, then we stop. We can also use the relative tolerance. That means if the ratio in the update is smaller than some threshold, then we stop. Finally, if the value of the function evaluated at xn is small enough, then we can also stop. So in practice, 3 different criteria are used in different occasions. So the first method is the bisection method. It could be the most simple method because we just need to simply cut the interval by half and half. The main idea is that on interval a and b, if fa times fb is smaller than 0, which means that if there is a sign change in this interval, then the function f must have a root in this interval, given that the function is continuous. So how do we do that? We just set c to be a plus b over 2. If fa times fc is smaller than 0, then there is a root in a and c. Otherwise, if fc times fb is smaller than 0, then there is a root in c and b. In either case, we can cut the interval in half and then repeat. So what if fc or fb or fa is 0? Then in that case, we just stop. We just exactly find the root. The second method is the fixed point method. So the fixed point method is based on the idea to find the fixed point for a function g such that gx equals to x. So if we let f of x to be gx minus x, or let g of x to be fx plus x, then finding the fixed point of g is equivalent to finding the root to f of x. If ga is smaller or equal than a, gb is larger or equal than b, then there is a fixed point for g in a and b. For the other circumstance, if ga is greater or equal than a, but gb is smaller or equal than b, then there is also a fixed point for g in the interval a and b. So that means for the function f defined as gx minus x, f of a is greater than 0, but f of b is smaller than 0. In that case, we are sure that f of x has a root. The fixed point iteration is simply to make xk plus 1 equals to g of xk. So if g prime of x, which means the derivative of g, is smaller than a constant rho, which is strictly smaller than 1, then the fixed point on the interval a and b exists and is unique. So in other words, if the derivative of g can be bounded by a constant rho, which is smaller than 1 on this interval a and b, then the fixed point exists and is unique. So finally, the fixed point method converges linearly. The other method is the Newton's method. Newton's method is the third method we introduced. The iteration formula is to simply make xk plus 1 to be xk minus f of xk divided by f prime, the derivative of f, evaluated at xk. We assume that at the root x, f prime of x does not equal to 0. In this case, the Newton's method can achieve quadratic convergence rate, which means that the absolute value of xk plus 1 minus x star is more or equal than a constant times xk minus x star squared. Finally, we introduced the second method. Because for the Newton's method, we need the information of the derivative, but usually we cannot directly obtain the derivative to a function. Therefore, we can try to approximate the derivative by the slope of the second line by xk minus fxk minus 1 divided by xk minus xk minus 1. So in this case, the iteration formula is xk plus 1 equals to xk minus fxk times xk minus 1 divided by fxk minus fxk minus 1. So we should pay attention that the convergence rate for the second method is not quadratic. The convergence rate is somehow strange. It is square root of 5 plus 1 over 2. Thanks for listening.